So our project is about novel porous organic polymer and removing dye pollutants from water. And I'm going to go ahead and zoom in. So what we're looking at right now is actually a poster that I'm going to be using in my classroom. So it's me hanging in my classroom. I'm also going to use it as an exemplar for science fairs. So I run science fairs. So they're actually going to be going over our rubric with this poster. So these are the two reactants we're using. So we have cyanic chloride and 2,4-diamino. It has a long name, so we're just going to call it 2,4-diamino. All right, so, and then here in the bottom, we can see that we're actually able to turn this level of dye pollution into, it looks pretty clear. So those are actual photos from our experiment. All right, so why do we care about removing dye from water? Well, dyes are a common pollutant for water. Basically, anything that you buy that is colorful, it's not just material it was, that's going to involve dyes. So fashion, paper, food, right, like your Fruit Loops, those are super colorful, cosmetics. Unfortunately, most of these dyes are toxic, so they are bad in use, so they can cause mutations, and as you know, cancer is a special suite of mutations, so they could also cause cancer. And what's one of the big jobs of DNA is carrying genetic information to the next generation, so they can also cause reproductive issues, both with organs, but also with, like, you know, since DNA damage, there's no guarantee that it's not your gametes that are being damaged. Also, for the actual, for you, not the future, it causes damage to major organ systems, so all the biggies, your liver, your central nervous system, your kidneys, so all pretty important. You don't want to be messing with any of those. In addition to the toxicity, they have ecosystem impacts. So dye is not clear, so when we're talking about an aquatic ecosystem, that's going to block sunlight, so that's going to reduce photosynthesis, which, you know, when you take out those primary producers, that's going to affect everyone. And this is kind of an urgent problem. Not only there's some pretty nasty effects, but if you've been paying attention this summer, like plastic production going way up. It's more than doubled since 2000. Clothing production is a big pollutant, right? Clothes are very colorful, and that industry has also skyrocketed in production, so it's more than doubled since 2000 as well. So you can see in this figure, we made a little over 40 million tons of textiles in 2000, and now it's like 120. So, you know, with the rise of like cheap and accessible clothing, that's great because it makes fashion more accessible to people, but that doesn't mean we're making a lot of stuff. That means we're making a lot of these dye pollutants. And the more of these pollutants we make, the more we can expect their harm to also increase. So let's talk about a little bit about the science here. Zoom in a little bit more. All right, so these special polymers can remove dye pollutants from water, and key ideas. Okay, not a typo. So what you're probably familiar with is absorption. So that's like what sponges do, so it's drawn into the substance. We're talking about adsorption. So like you have to enunciate obnoxiously. So adsorption, and things are only attracted to the surface. So this is like how paint works, right? When you paint your wall, hopefully like you don't do a cross-section of your wall and it's all like red or whatever color you painted it. So this is only the surface. And how it works is dyes are going to stick to the surface of it. And I have a little illustration there with that one letter difference, and they do kind of sound the same. So again, you just have to super enunciate. So here is adsorption. We're only sticking to the surface. And then absorption where it goes through. So today we're talking about adsorption, so only the surface of the materials. All right, so our project, let's see if I can get a little bit zoomed out here. So our project combines, the reason we picked these two products is they've been used before to make successful absorbents, but they've never been used together. So like, you know what, this guy's great, maybe we're gonna make a dream team together. And we're targeting specifically crystal violet dye. So another thing that's good about this combination is we expect our product to have a negative surface charge, and the dye is cationic, which means it has a positive charge, so you know opposites attract. And our produced polymers is going to have a high surface area, And remember, since we're talking about things sticking to the surface, the more surface we have, the better that is going to be. So it has a nanoporous chemical structure, which means there's going to be like a lot of little pores for things to get stuck into. Think about, when you buy the cheap paper towels at your school, you look at them, they're basically smooth. You could roller skate on them. But like, you get those thick, fancy ones from the store that cost like 5 times as much, and they're quilted, right? Like, that increased surface area is going to increase the effectiveness. So we're looking to make a high surface area material. So we're going to talk about making it. So in order to test it, we do have to make it. So I have a set of illustrations talking about the synthesis process. So basically we need to prepare a solvent. So we're dissolving them in DMSO. And we make 2 beakers of DSMO. And then we weigh our reactants. We're doing a 2-to-1 ratio. So we have 2 millimoles of 2,4-diamino and 1 of the cyanic chloride. And we're going to add each reactant to one of the prepared beakers. So we're adding them separately, each in their own little beaker, and we're going to stir them up with a stir bar. And you want to wait till they're completely dissolved. So we're dissolving them both in solution, and then we are going to be combining them. But before we do, we're going to add a neutralizer. So we add triethylene to the 2,4-diamino because we don't we don't want any hydrogen release and like making any acidic. So we're going to add a neutralizer, and then we are going to combine everything, and it's going to form a precipitate. So we did this in a round bottom flask. And then we put it in a hot oil bath, and we heat it to 140 degrees Celsius. So basically, we want to add heat so that it's going to improve the reaction, right? So like, basic chemistry, more heat, more stirring, you're going to get more reaction. But what happens when we heat up liquids?
They boil. Yeah,
they boil off, and we don't want that. So we actually also added a condenser to maintain the solution volume so it didn't boil off. And then we are going to clean that product. So basically, we put it through a filter. We have a little filter paper. It looks like a coffee filter, but fancy lab one. And we rinse it, after all the DMSO drains out, we rinse it 10 times with deionized water, and then an additional 10 times with ethanol. And if you want to rinse it 15 times instead, that's fine too. There's like not too much rinsing, but the minimum is going to be 10 times. And that's to open pores in the product. So basically, we're making all these little pores, but they could be clogged up with DMSO, so we're going to flush them out so that we have that surface area available to act as an absorbent. And then we're going to go ahead and dry it out in an oven for at least 8 hours in a vacuum oven. And then we're going to crush it up after we get it out of that oven to make sure that we don't have any aggregates. And then we need to make sure that we made the right thing with FTIR. So we're going to actually skip down here to characterization. So before we go through all the trouble of testing it, we want to make sure we actually made the right thing. So I'm going to zoom in here. Maybe, yeah, there's my button. All right, so we're going to zoom in here. So here we have, so we did FTR, so that uses infrared light to scan, to shoot it at the product. And basically light's going to bounce back depending on what it is. It's like a fingerprint for chemicals. So here are our 2 reactants. So you see they have different bumpy parts. This one has different bumpy parts, just like when you take a fingerprint, you have different swirls. And here are our reactants. And you can see, so we made 3 different versions of a reactant. Basically let it run for 8 hours, for 16 hours, and for 24 hours to see if there's any difference in quality, because we're trying to min-max our product where we have the minimum effort for the maximum results. And you can see these 3 top lines, they look very similar. They have peaks in the same places. And the other thing we're looking for is we do not want our products to look exactly like the reactant. So here, we don't have any peaks here. So in the 2,4 we have it, and then in the products we don't. And then, so they don't look exactly like the reactants, but they do kind of look like an in-between of them, and that's exactly what we're looking for. So it looks good. It looks like we made the right thing. And we also did SEM microscopy to check the particle size. So you can see here, this is 1 nanometer, so we've got particles smaller than a nanometer, smaller than 500 nanometers. And for it to be considered nanoporous, the pores have to be smaller than 200 nanometers. So if the particles are smaller than 500, then we can expect the pores to be smaller than 200. So just making sure that we actually made a nanoporous material. Now that we're happy with what we made, we're going to go ahead and talk about how we tested it. So we tested 4 different aspects of exposing it to a dye to see how absorption goes. So we tested all 3 of our different products. So we made let run for 8, 16, and 24 hours to see, what is the best time to let that reaction go. And then we tested how much of the product we added to the dye, so between 10 and 50 milligrams for 10 ml of the dye. And then we tested how long should we let that absorbent mix with the dye, how long should that exposure be, and then we tested how much dye can we remove. So we did more dye and less dye, so between 5 and 50 ppm. And this is how we did it. So we prepared, so we made some crystal violet, we prepared 100 ppm stock solution, and then we diluted it down to whatever we're testing. Remember, we're doing several iterations here. And then we reserved a sample of stock solution for comparison to use as a control. So we prepare our dye, and then we're going to weigh our absorbent, and again, we're doing different weights depending on the trial we're talking about, and then we just add them together and we stir them up. And we're going to time them, so we let them go for a set interval, just different intervals of time. The shortest time we did was 30 minutes, the longest time we did was 3 hours. And then we want to stop that absorption because remember the time matters, so we're going to stop it by spinning it in a centrifuge and removing the powder. So we ran it in a centrifuge for about 10 minutes, and then we did UV vis. So basically, UV vis, the more dye there is, the less light that's going to transmit. Remember, that's one of our ecosystem issues. So we're going to be testing it, so we want it to be more clear, and the UV vis is going to tell us that. So we run our samples and controls, and that's going to basically tell us effectiveness. All right, so let me zoom out a little bit so we can see the fullness of these slides. Okay, there we go. Okay, so I'm going to talk about the different tests that we did in those applications. So first we tested dosage. So we did 20, 30, and 40. And I didn't talk about the reaction test, but the 24-hour one was the best in terms of both the effectiveness and like how much product we got out of the reaction. And then also we did an initial one, and we're like, this one is going to be removing the most dye. So you can see here, here's the stock ppm. See how big that peak is? So it's blocking a lot of light. And then here, the blue, that's the 40 mg. So as you imagine, the more absorbent we add, the more we're going to be able to remove. Just think about it. If you have like a bunch of paper towels versus a little bit of paper towels, right? You can be able to soak up more. And here we have an efficiency graph, so translating these to efficiency. So they all worked pretty well. So even at less than 30 mg, it still removed over 50% of the dye. So not bad, but we have 100% removal with that 40 mg. And here's actually a photo of them after they're exposed to the absorbent. So here we have that 40 mg. I mean, like you look at it and the only thing that you can see that's colorful are actually little particles that have the dye soaked into them, little particles of absorbent. And then here we have the 20, the 30, so backwards. So here we have the 40, here we have the 30, 20. And then this is going to be the stock solution. So that's how it looked before we added any absorbent, so that's our control. So that is very satisfying, right, because you can tell right away that it worked, but unfortunately we do have to use UV vis because it looks less purple is not acceptable in the paper. So we did concentration tests as well, so this is where we changed the amount of dye that we added. So we have from 1 part per million to 50 parts per million, and we used 40 mg for all of that, and we ran them all for 2 hours. So here's our image, and you can see, as you expect, the 1 ppm is already pretty light. So this is after absorption. And the 50 is still pretty dark, so it still looks pretty dark. So as you expect, the more dye you have, the less efficient it's going to be at removing it because we're not changing that dosage. So it's still 40 mg, and that 40 mg and that 50 just has to work a lot harder than that one in the 1 ppm. So at one, so The removal efficiency here, we're only sitting at about 40% in the 50s. So it's still making a big dent, but if you can see here, up here, we're going, once we have those lower ppms at 1 and 5, we're looking at way over 90% efficient. So, and then for kinetics, that's what we call absorption time. So basically we're exposing the adsorbent to the dye for different amounts of time. The longer that you set it, as you can imagine, the more dye you're going to remove. So here we have the stock, big peak, and then here we have the different times. So 3 hours is pink line, and it's pretty flat, so it is fairly clear. You can see that too in the image here. So this is the 3-hour one. And then we have the 1.5 hour one. If you notice, it is not included because it's kind of an outlier here. It's not on that gradient you expect. And then here we have the 2 hour, the 3 hour, and then the stock. And if you look at these peaks here, they're very close to each other. And if you look at their removal efficiency, like they're all actually pretty efficient. So even at 30 minutes, we're still getting like over 80%, I think it's 89% of the dye removed. And we've got 99% removed after 3 hours. So time doesn't seem to be as big a factor in terms of how efficient it is. All right, so discussion. So what do we think about all of this? So this is pretty promising. So it does work, and it does seem to be pretty effective. And the nice thing about the products that we made is it's pretty inexpensive and simple to synthesize. So it's like not harder really than making sweet tea, right? So we're just taking a solid and we're dissolving it in a warm liquid. You just have to, it's a little bit warmer than you're probably making your sweet tea at home. And like, I don't know, maybe you are extra, maybe you do brew for 24 hours. I'm no judge. But it is really simple to synthesize. Like, you know, you could do this in a home kitchen even if you desperately wanted to. For possible future directions, we would want to look at more advanced synthesis techniques. So we could try something a little bit more complicated in terms of synthesis, and that could yield a higher quality product, which may be more effective. We could add functional groups, which is, again, we're looking to increase the effectiveness. So something that's going to be more basically little helpers we can add to help target the dye pollutants. And we want to basically reduce cost per use, so maybe looking at a way that we can reuse the absorbent and then like how effective that is. Like, you know, when you use your bath towel at home, like you probably don't throw it away after one use. So can we reuse these would be one of the big questions for the future. So this is very exciting because like obviously cancer, bummer. So is brain damage and liver damage. So that's really exciting that this could potentially address those issues. And here are acknowledgments. So everybody who organized RET both now and in the past, and everybody in our lab, Dr. Bowie, Jessie, Min, B, everybody in her lab helped us like past 6 p.m. some days, helped us figure out everything, and it was really amazing to be part of this team and supported and just treated like anybody else in the lab in terms of, you know, expectations of competency. Here's a little photo of me, my research partner, and the grad student who, or the postdoc who mentored us.